Okay, for our second talk of this morning, we have Arnav Jhala speaking on dynamic discounting in decision making.
Good morning, everyone. Thank you all for showing up in the first session this Sunday morning after the Saturday festivities. So this work is primarily my graduate student Eric's work. And we started with this notion that as humans gain more experience and more skill, does it change the way they approach problem solving? And in the domains that we work in, which is real-time strategy games, decision making in complex environments like StarCraft, we connected this to the idea of planning and confidence. So as players gain more skill, they have more confidence in future rewards, and so they discount their future rewards more. And this has been studied in human decision making quite a bit. For those of you who know the marshmallow test, I actually interestingly snuck in one yesterday. So when I was session chairing, I mentioned a YouTube video before Sadaf's talk. And I was actually wondering how many during the talk looked up that video, right? Because there's the immediate reward of looking at this funny video on YouTube. But then the sort of the longer term reward of actually like missing one or two slides and actually missing some key concept from that talk when you get to the end was the trade-off, right? So I don't have IRB, so I can't actually ask you to raise hands. But the idea of the marshmallow experiment for those of you who may not be familiar is that the participants were given a marshmallow and then the experimenters left the room. These were children. They were told that they could eat the marshmallow and walk away, or if they waited for some amount of time, then someone would come in with another marshmallow and then they would get two, right? And what they found was that a lot of humans actually little humans actually just ate the marshmallow and left because they could not wait for that second marshmallow. So they were discounting the benefit of gaining, double the reward after a certain amount of time. And so this behavior is referred to as delay discounting. And so the idea is that in decision making, humans often, depending on how much confidence they have in a future outcome, will take risks. And so two other humans might choose lower immediate reward in order to eventually get a higher reward later on. So we started looking at how this particular concept is represented in our some of our decision-making systems, right? And especially in the domain of games that we work in, reinforcement learning-based approaches have been popular. And so if we look at how the mechanism of reinforcement learning works, there is a discount factor that is in most algorithms. However, this is largely not fully expressed or sort of teased apart. Usually the default geometric discounting is applied. And so we wanted to explore in this work whether more human-like discounting behaviors that were observed by psychologists in human studies actually have any impact on the way our agents behave in their environments. And in particular, it has been found that humans often use either exponential or hyperbolic discounting rather than the linear geometric discounting that are in our AI models. And this is taken from Green, Leonard, and Meyerson, which shows sort of and a lot of this is done in the field of economics. So we just started chasing the money, and we found some of this really interesting work. This study sought to find which discount function best fits how participants devalued like a $10,000 reward over time. And so it was actually found that exponential hyperbolic is what a lot of humans, in that study at least. Now, reinforcement learning agents, they learn a policy through direct interaction with the environment. So they're learning a reward. However, the interactions are immediate and the rewards are immediately observable. So part of the problem is that a lot of problem domains have agents that are cumulatively adding a lot of immediate rewards. Of the two main families of reinforcement learning algorithms, the value-based approximations and the policy-based, we will use the policy-based one in this work, but the overall idea could apply to the value-based one as well. So the general idea in RL, and I'm going to be quick in mentioning this, is that this expected reward function is geometric. And the idea is that it converges to the net present value, which is found in the economics literature. There's also another concept, which is the learning rate. And this also affects how policies are chosen by agents. And a learning rate annealing or adaptive learning refers to the changing of learning rate to improve performance of an agent. So based on this, what our approach to this was that discounting behavior is related to how much confidence an agent has in future decisions or likelihood of getting a future reward. And so we defined a confidence metric, which given a state S for an action A, if there is a current policy, then this pi signifies how much confidence the agent has in that policy achieving an immediate reward and a future reward. And so the idea is that we use this confidence to then vary the discount factor, vary the discount rate, and vary the learning rate. And then the idea is if we make this adaptive, how does that affect the behavior of the agent as well as the performance? So talk a little bit about real-time strategy games. They are two-player, zero-sum military simulation-like games. They're often played on a grid. Each player builds and commands an army. Objective is to defeat the other opponent's base. In this particular domain, one of the reasons we started looking at this delay discounting behavior is because some of the early work we were doing was in goal reasoning. And we started looking at long and short-term goals in a real-time strategy game. So sort of building up a particular strategy for attack units and defense unit versus a longer-term strategy of, say, doing a particular type of rush with a group of units. And while our agents were learning how to create these goals, a lot of times your games will have one goal at the end, win or loss. And so how any particular strategy executes is dependent on a lot of complex sort of situational factors in the game at any particular moment. And there was a lot of thrashing that happened in agents because they would start executing a longer term strategy, but then due to some event or some reaction that the opponent gave, they would then switch the strategy, but then they wouldn't be able to then go back to a strategy because they had overcommitted resources to a different one. And so human players are able to then persist a bit longer, even though the immediate rewards are not coming because they know that they can recover. Right? So that's sort of where this whole idea of delay discounting came up, was due to our work on goal reasoning there. This community is quite familiar with this domain. We've seen a lot of work I'm just going to quickly mention, though, that real-time strategy games are interesting because, first of all, they require quick decision-making. Like I said, short and long-term goals need to be balanced. The decision space is large and exponentially growing. So it's nearly impossible to actually write out policies by hand. But what's more important that these are simultaneous move games. So unlike a lot of turn-based games where there is enough time to think about, to observe what the opponent did, then think about it, and then execute the policy, you actually have to continuously move because your opponent is continuously moving and simultaneously moving. For this paper, we are focusing on a very specific type of game which captures the type of behaviors that we are trying to characterize. And this is capture the flag. So capture the flag is a game where the two teams need to capture the opponent team's flag and bring it back to their base. What's interesting, though, is that a lot of times in capture the flag, as it is in sort of football, soccer, and so on, a lot of the immediate rewards are sort of getting the flag and then keeping control of the flag and then switching the flag out to teammates and then defending your teammates so that your flag has more control. Now, what ends up happening is a lot of times agents, when they learn this, they go for the immediate reward of controlling the flag. And what that does is that it sort of delays the actual return of the flag because they are constantly trying to get away from the enemy while controlling the flag, and they get into this situation where for a long time they're controlling the flag, so that's really good. But then they're not actually winning the game because they haven't returned the flag. And so the final reward is right at the end over there, and there's a huge reward for that. But then a lot of these local rewards make the agents sort of less efficient. By the way, this capture the flag domain is part of this framework GIM micro RTS that Santi Ontanian and Costa Huang have made. And the GIM RTS part is that we have not just the full RTS game, but also several other subdomains to explore these specific questions. And so we've contributed this to the open GIM micro RTS community, so other researchers can also use this game for their studies. So for now, we are using a 9x9 map with a flag in the center. One round lasts for about 2,000 time steps, and it's trained. The agents are trained via self-play, as is the trend. And there are big rewards for winning or capturing the flag, but sort of smaller rewards for also maintaining control of the flags. So with this setup, we now start looking at a number of different experiments that systematically look at the three different aspects that I mentioned. The discount functions. So the first set of experiments is based on three discount functions individually, so geometric only, and it's fixed throughout the gameplay, hyperbolic and exponential. The second set of experiments looks at discount rates. So the discount rates are either static throughout or dynamic based on the state of the game. And then finally, learning rates as well. And these are the three discount functions. I mentioned them earlier. Overall, we see that even though, so this sort of the top line on your left, the average episode reward is actually pretty high for the geometric agent, which is what if we were doing kind of a typical RL paper, we would say, oh, here we have an agent and it does really well, it converges, great. Except that the actual flag returns are really bad for that agent over the time period, right? And so what we are trying to, we were actually kind of a little bit surprised. I would have thought that the results would have been closer. And so if we look at a little bit at the attacks issued and so on, and units produced and we see that the geometric agent actually is doing a lot of work, just not winning, because it is going for these immediate rewards. Um, and so, so that sort of holds up in our experiments. If you look at like flags grabbed, right? So even though like time holding the flag is 545, uh, the grabbed flags is only 8. This is because once the flag is grabbed, then for some amount of time, they're just trying to maintain control of the flag without actually returning it, which means that going back and grabbing it again doesn't happen much. So that was sort of the first. And just if we use just those three, then we almost immediately now in this experimental setting see how sort of just looking at the rewards is not enough in terms of behavior. The second set of experiments we did was using different discount rates. So there's the sort of just the static rate. Then we have an increasing one. So this is kind of related to yesterday's paper about sort of switching goals as the task time increases. So over time, we start discounting future actions or future rewards more. And then the confidence-based one, which is based on our confidence metrics assessment of the situation and then choosing the discount rate that is applicable in this particular game context. And there we see that so that on the top left, which is the average episode reward, the top line is the one with increasing discount rates. So overall average episodic reward is the best for the treatment where the discount rate is increasing over time. The static one stays pretty low. And that could just be a factor of just the fixed static 0.99 number that we chose. A different number would have given a different one, but it's generally pretty. And then the confidence one sort of has, again, it's kind of an average episode reward is in between the two. But again, if we go back to the flag returns, which is sort of the longer term goal, the confidence-based metric one does best pretty consistently, and it also converges faster, fewer runs. By the way, the x-axis is sort of runs, and it sort of goes to like 9 million-ish runs. And so in this case, we can see that sort of, increasing is definitely better for rewards. Increasing is okay in terms of flag returns. The static one just underperforms on both metrics. The third set of experiments we did was on learning rates. So there's sort of a linear learning rate based on timestamps. There's also a decreasing learning rate, and then again the confidence based one. In this case, what we see that the average learning rate again, or the episode reward again on the left side, the linear one gets higher reward. So this is pattern kind of consistently stays. The confidence-based metric one also gets pretty good rewards. But at the same time, the one with the decreasing one actually has more flag returns. And so there what we can maybe say, and this learning rate one is a little bit unclear how to fully interpret it. And so we are looking into this a little bit more, but ideas on sort of how to explore or understand sort of how to interpret the way rewards and flag returns are done in learning rates would be an interesting discussion that I'd like to have. And here sort of in terms of the attacks issued and the actions that agents do, they're actually pretty comparable. There are no drastic differences between the way these three agents approach these actions. So to conclude, we are trying to better characterize this notion of short and long-term rewards and how they're balanced within RL agents by looking deeper into this distinction between discount rates, how they're chosen, so that we can better understand what our agents are doing, better understand how to model humans when they're doing, and then sort of dig a little bit deeper into our reasoning process that we use for this. The results of this specific set of experiments suggest that this could be a viable option for modeling human discounting if we are looking at RL agents that are modeling human data. But there's a lot to explore. It's just the beginning of this research thread. There are a couple of limitations that we would like to mention. One is that random initialization of our network weights can significantly affect performance. The overall trends remain the same, but the exact numbers I wouldn't look too deep into. And the work is focusing mainly on the behavior of our agents, not necessarily the optimization, the low-level optimization of rewards and so on, because we were just trying to, at a high level, understand the differences between these algorithms. And that is it.
So there's a social psychologist at Columbia, E. Torrey Higgins, that rejects this notion that motivation, at least in humans, are fully explained by reinforcement or in terms of pleasure and pain or carrot and the stick. Instead, he says that humans are motivated by being effective in our life, and there's three kinds of effectiveness. It would be value effectiveness, truth effectiveness, and control effectiveness. The first being that we're good at achieving our goals and getting the outcomes we want. The second is that we're good at ascertaining what's real in the world to some extent. And the final one is being effective at performing the actions that we're attempting. How would you respond to that? Is there some way to incorporate those kinds of factors into it more than just reducing it to a reward number?
Yeah, I think that's really interesting. I would really like to look at that work and see how it could be incorporated. It seems to me that yesterday in the paper that was talking about the reefs, right, where there were anomalies. They were looking at how we agents might change their goals, right, based on preferences. And so one of the things that we're looking at is modeling what's called preference reversal. And I can imagine that these preference reversals could be in terms of like the three categories, right? Like, do I value how smoothly I do this versus how efficiently and so on, right? And so depending on what the agent values, now what representations we might use for those entities, I wouldn't know, but it would be interesting to see if we can have different behaviors of agents based on that theory.
Yeah, I'll send you a pointer. He wrote a really interesting book called Beyond Pleasure and Pain, and I'll give you a pointer to that.
Thank you. Hey, Dustin.
Thanks for the talk. So just going back to the results, just to double check that did you say that the discounted, when you used the human preferences, did it outperform the like non-human discounted methods, or were they just separate results?
Well, so in
terms of like overall flag returns.
Yeah, so overall the trend was that the geometric and the hyperbolic, the hyperbolic and the exponential ones that have been found in human, they outperformed in terms of total wins.
Right. Okay.
But not quite just average episode reward.
So I think that's a really very interesting. It's a great result. How sensitive do you think it is to the design of the reward function? Because I know for RL research, they spend a lot, and maybe this addresses your limitation, but they sometimes you can spend a lot of time designing the right reward function. And I wonder how much that might impact this, whether this would still work if it was, I don't know, a different reward function.
It would, yes, absolutely. The design of reward function is key, right? And so the question though here is that how would you then design reward functions that take into account rewards across multiple time scales and across multiple competencies, right? So we need some way of kind of saying, so there isn't a clear sort of way to do that, right? And then we can hack into individual domains and optimize there, but in general, we wouldn't know. And so, yeah, that's.
Yeah, thank you.
So this is going to be reminiscent of a question I asked yesterday.
Yeah.
Look at your rates of learning there. How do they compare to human rates of learning in the same domain? I assume that people learn much more rapidly. They don't take
People learn
millions
much
of trials,
more
right?
rapidly, yes.
Okay,
Yes.
so given that we have for over 30 years had computational models of human learning in sequential domains that do learn much more rapidly, why in the world would you start from reinforcement learning and try and improve it? Why not take some of the work from, say, the 1980s and through the mid 90s on learning in problem solving domains and look at those and try and use those to handle these real-time strategy games? What in the world motivated you to use reinforced learning, which is obviously not the way people do these things? And ACS again we don't care about fitting reaction time data, but we want things that are roughly human-like. This is not human-like. What's your motivation?
Yeah, so I guess here the real-time strategy games was mostly a domain where this capture the flag has characteristics of the type of domain that we wanted to
I have
explore.
no problem with the domain. I'm asking about the learning technique.
The learning technique, yeah. Well,
if you need pointers to some of the other alternatives, I'd be happy to share them with you.
yeah,
But there are plenty of them.
we should definitely look.
All right.
The idea though is that we want to understand. So for real-time strategy was StarCraft, for example, right?
Yeah.
So this is a much smaller domain. But StarCraft, for example, it would be nearly impossible to sort of. We don't understand how top StarCraft players learn, and we have observed them and so
No,
on.
but in other
It's very
domains,
hard
there's plenty of evidence that
But in other domains.
humans learn new structures rapidly. Yes, they may use statistics to evaluate them and to refine them, but they don't do this. And so I just encourage you and your students to get off of this kick and look at the computational approaches to learning much more rapidly. That's my.
So
my
next year.
We'll talk.
Excuse me. I think my question is much easier.
I don't have to write a whole
paper.
paper, submit next year.
The task for reinforcement learning is to optimize their long-term or short-term reward. So the algorithm only knows the reward is what it tries to maximize. So now it seems like you're looking at all of those different ways to maximize another metrics that your RL algorithm is not aware of.
Yeah.
In this case, of course, it's a nice matrix. It makes sense for this task. But if it's a random, you could have, right? Because the algorithm doesn't know like what other metrics are good. It could have optimized another metrics, which has no benefit for the task. So I guess my question or my comment or my thought goes to like how, again, like I like this flag return thing, but how do you justify that this sort of adjustments to the parameters will always do beneficial thing to ARL in a different context?
Yeah, so this is somewhat related to Dustin's question too, right?
Exactly.
Which is, so I will say that the claim is not that this will always be better. The claim is that there are other ways in which we can express, even with these RL agents, their behavior. And And for different domains, we want to be able to characterize their behavior and their decision making, which we don't have a view into. And there may be domains where there are rewards, sort of these rewards at different time scales. Humans are able to handle this pretty nicely, right? But what are the cognitive mechanisms that make humans do this efficiently, right? And so this is trying to map that kind of representation to our sort of our formerisms that we know. And discount functions basically hadn't been explored in this detail. So we were just trying to look at whether there is any signal. And yes, capture the flag was very conveniently designed task so that we can get strong results. I will say that. But so I don't have an
Yeah,
answer.
let's talk more offline.
But yeah, so the concern is real, right? That the thinking is, what if we just said flag returns was the metric, right? Then you would create an RL agent that wins, right? And optimizes that metric. And so if we choose whatever the reward function is, it's going to optimize that. Here, what we're trying to do is that if there are actually rewards at different horizons, then what is the mechanism that we can use so that we can capture those without having to explicitly express them at every single scale? Here, it's just two scales, right? There's sort of the flag captures and the immediate sort of rewards of controlling the flag, right? But in StarCraft, for example, there are several.
All right, so that's about all the time we have, so I want to thank the speaker again.